Hi, in this video, I want to give you an overview of the geology of petroleum. It's an interesting geological story and one that I think is important to understand, regardless of your views on uh, the ethics, if you like, of using petroleum. If we start by looking at the chemistry, crude oil is a mixture of um, different types of hydrocarbons. A hydrocarbon is a chemical structure that bonds carbon and hydrogen together in chains then of different lengths. The shorter the chain, the lighter the hydrocarbon, the longer the chain, the heavier it is. For example, the shortest chain, methane, gas, is CH4, one carbon, four hydrogens. Tar would have a whole long chain, lots of carbon, lots of hydrogen bonded together. Crude oil then, it's really quite remarkable stuff. It contains a huge variety of different materials that will be separated by fractional distillation. But if we think about where it comes from, its origin is from plankton, these microscopic marine organisms floating around in the sea that, when they die, sink to the seabed and become deposited in the rock. We can see examples of these planktonic blooms in modern marine environments. When they die, these animals and plants sink to the seabed and form this organic rich mush, for want of a better word. This can be then food for bottom feeding animals, from benthonic organisms. But if we have an anaerobic environment, we don't find these scavenging organisms, these detrital feeders. As a result, this organic mush will accumulate. Over time, as it becomes a rock, with deposition of sediment on top, a bit of pressure, that turns into a rock we call a black shale. Black because of its carbon content, its high carbon content. With burial, the rock comes under pressure and some temperature. That starts then to change this organic material. We see, first of all, the formation of a solid hydrocarbon, a waxy-like substance called kerogen. This diagram here we call the oil and gas window, shows us the temperatures where this occurs. So you can see that kerogen is going to form at relatively low temperatures, so less than 60 degrees. When the temperature gets to about 90 degrees centigrade, this kerogen then is changing into a liquid state. The hydrocarbons are getting shorter as the heat breaks the bonds between these hydrocarbons and turns it into a liquid that we call oil. At higher temperatures, the hydrocarbon chains are further broken down into shorter hydrocarbons, and these then become a gas, methane. And we can see that there are different temperatures at which these different materials reach their peak productivity. Now, this is all happening in this organic rich black shale, the source rock uh, for our petroleum. This liquid and gas hydrocarbon then is less dense than the rock that it's formed in, and also less dense than water. So it'll get squeezed out of the original source rock, which you call a primary migration, and it'll find its way then into a permeable rock and start to migrate upwards. The analogy here is like these air bubbles released by a diver. They'll find their way upwards because of this density difference. And it'll keep rising until something stops those hydrocarbons from moving. Now, most oil, or most hydrocarbons, should I say, are formed back in the Jurassic period. At that time, we see Pangaea starting to break up, sea levels are very high, and as a result, we get a lot of shallow marine environments. Where these black shales form are where today we have our major oil fields. And we can see they're distributed in lots of different places around the world. Even here in the UK, we have oil in the North Sea area. The source rock for this oil is a rock unit we call the Kimmeridge clay. This is a cliff on the south coast of England, a place called Kimmeridge Bay. And you can see just how black this shale is because of this very high organic material. This same rock unit underlies much of the North Sea oil basin. Now, for oil to actually accumulate in significant quantity, we need to have the right combination of rocks and also the right structure. So we need to have rocks that will act as a source of this oil, or source rock. The oil then needs to migrate through a permeable rock and accumulate in a permeable rock we call a reservoir rock. There needs to be some type of structure which allows that oil to accumulate. And then we need to have a cap rock of an impermeable rock above that structure to actually prevent any further upward migration of the oil. If there's no cap rock, if there's no nothing to trap that oil, it will continue to reach to the surface to form what we call an oil seep. But these structural traps for oil are really important in the story of how we get enough oil accumulating for us to be able to extract. So the reservoir rocks in which the oil accumulates need to be permeable and porous. There need to be gaps between the grains in the rock for fluid to accumulate. And also to extract this material, we need to be able to have these pores being interconnected. If that happens, oil can accumulate in the rock, and also oil can be extracted from the rock. If permeability doesn't exist, sometimes we can use hydraulic fracturing to create that permeability, to break the rock up underground, to liberate the fluids that are trapped within. There are several different types of hydrocarbon trap. These are structures that allow hydrocarbons to accumulate. This is the simplest of them, what we call an anticlinal trap. And here we can see our three rocks: our C, our source rock; B, the reservoir rock; and A, the cap rock, occurring in the right sequence and having been formed into an anticlinal shape. This creates a dome where, as oil and gas is migrating upwards, will allow that gas and oil to accumulate. Notice how they're stratified by their density. We see other structures as well that can create this pocket for hydrocarbons to accumulate. This one is called a fault trap. Here we can see the reservoir rock B has been faulted and displaced, so that the cap rock has been down thrown there to create a seal across the end of the reservoir rock. This can allow hydrocarbons to accumulate if the fault itself is impermeable, which can happen because faults can be pathways for mineralization to occur, and that can often seal the fault to prevent leakage of these hydrocarbons to the surface. Our next hydrocarbon trap is a salt dome. Salt domes are caused by a low density salt being sort of stoping its way up through the surrounding rock or the overlying rock because of its low density and its ability to flow. This again will dome up the rocks around, a bit like in an anticline, and it also provides a seal for the end of a reservoir rock. The salt itself acts as a very good cap rock. It's impermeable, and it'll even, as it flows, it can heal any cracks that form within it. The hydrocarbons tend to be trapped at the side of the salt domes, but there can be antiform or anticlinal traps above the salt dome itself. The final type of hydrocarbon trap we need to consider is a stratigraphic or an unconformity trap. It's quite subtle in this diagram, but again we have our source rock as C, our reservoir rock as B, our impermeable cap rock as A. In this case, that cap rock is sitting immediately above an unconformity. This means that the cap rock there will cut across the reservoir rock, sealing that reservoir rock to allow the oil and gas to accumulate. So, once we have determined the traps in which oil can be formed, or can accumulate, should I say, it's then time to drill. Drilling is an incredibly expensive business. It can cost millions of pounds or millions of dollars for a well to be sunk, particularly in a deep or in an offshore oil field. Understanding the geology is really important to avoid massive expense for no return. Now, oil is sticky stuff. Where an oil field has been discovered, very often, most of the oil won't be able to be extracted from that oil field because oil will stick to the grains within the rock. There are techniques that are used to try and enhance recovery. It could be pushing water down into or pumping water down into the reservoir rock to push the hydrocarbons up towards the well. This particular example looks at injecting steam into the oil to reduce its viscosity. This, though, can be very energy intensive. Other ways might be to increase the permeability of the reservoir rock by doing some hydraulic fracturing. We do know where the world's oil is. The green areas on these maps show the various oil fields. The darker they are, the more oil occurs there. Whether we should then go and exploit all of these is a topic for debate by policymakers and for the people who elect them. There are, for example, large oil reserves, almost certainly, in the Arctic part of Alaska. Debate about whether those reserves should be exploited has been going on for years. Whether the oil in the ground should stay in the ground to protect the pristine environment and wildlife that exists above is something that's been discussed and debated, and I'm sure will be in the future. What do you feel? What do you think about that? Should this oil stay where it is? A geologist called Hubbert made a prediction about oil fields, how their production will be on a bell curve. And at some point you would reach what he called peak oil. His prediction for US oil fields was that this would arrive in about the year 2000, followed by an energy crisis as oil production fell dramatically. Interestingly, the occurrence of peak oil always seems to be a little bit in the future. Predictions of peak oil at the moment stretch from about 2019 up to about 2040. Hubbert didn't know about the improvements to technology and our ability to find and extract, particularly unconventional oils. But there's another pressure on this as well. Our understanding now of the impact that petroleum and our reliance on it has on the climate. We may yet get to peak oil. We may even have reached peak oil. But it may well be driven more by our choices and our policies rather than by the geology. There are various other types of unconventional oil sources. These are the tar sands in Alberta in Canada, where oil has been trapped within unconsolidated sand near the surface, and it's actually mined out. This is very energy intensive, though, to then separate that usually quite heavy oil that's left in the sand from the sand to actually turn it into a usable product. It's energy intensive, expensive, and has a massive environmental impact. The amount of oil it contains is huge. I, for one, am not particularly sure that we should really be exploiting that resource. So, as we see the sunset over an exploration rig, oil is remarkable stuff. the things we can do with it are very, very varied. But the cost of that, certainly environmentally, is very high. As geologists, we know the sequence of processes required to form, for it to migrate, for it to accumulate, and for us to be able to find and extract it. In the future, we'll need to decide whether that's something we should do. For now, though, it is something we rely on. Our civilization relies on exploiting this incredible resource. But for the future, we will have to find some alternatives. If you have any questions, bring them along to class. I'll see you then.